Okay, so have another look now at this last derivation where we calculated the GCD, the greatest common divisor of 6, 12, and 93. The Greeks would have thought about this kind of thing geometrically. They like to think of number operations corresponding to geometrical patterns. So they would have thought of a line segment that was 612 units long, another line segment of 93 units long, and they would have imagined you being able to, just being given these line segments without knowing these things here, and trying to find a sort of commensurable segment. In other words, to try to find a segment such that this one was an integer multiple of that segment, and so was this one. That's one way of interpreting that. What we've done is a line segment which was of length 3 in this scale would have the property that this one was a multiple of 3, and this one was also an exact multiple of 3. And this was sort of the biggest line segment that had that property. So when we do something like this, dividing one number by another, we could have done that geometrically in the following way. Okay, 612 is a lot bigger than 93, so let's make it a little bit more accurate. So there's our 612, and maybe there's 93 in comparison. Okay, so they would have said, all right, we can imagine this like a rectangle here, and what we're doing is when we divide 612 by 93 is we're taking out a square. That's a square. That's sides 93 and 93. So you're just taking out one square, a second square, a third square, a fourth square, a fifth square, a sixth square. 1, 2, 3, 4, 5, 6. And then there's something left over. What's left over? A new rectangle, and this portion here will be the remainder. It's a geometrical way of expressing 612 divided by 93 is 6 with a remainder of 54. So from the original rectangle of sides 612 and 93, we now have a new situation where if I put it on like this, where that's 93 and that's 54. And then we just repeat. We just divide by taking out squares. In this case, only one square. It should probably look more like this. So that would be one square, and then a new leftover thing. That would be the result of the basis for the next algorithm step. And there's quite an interesting consequence of this algorithm that they probably would have discovered from this geometrical way of thinking that leads to a very nice topic called continued fractions. And I want to just illustrate that with this example here. Continued fractions. Okay, so let's have a look at this. Another way of interpreting what this is to say, well, what we're doing is we're saying that 612 divided by 93 is actually 6. 6 plus a remainder of 54, so 54 over 93. That's another way of saying this divided by this is that's the quotient, and that's the remainder. The remainder is less than 1. Now what we're doing at the next step is to divide 93 by 54. So what we should do arithmetically to sort of correspond to that is we should think about rewriting this as 6 plus, we'll write 1 over 93 divided by 54. That's a legitimate operation. 54 over 93 is the same as 1 over 93 over 54. And when we write it like that, then we can write it as 6 plus 1 over, what's 93 over 54? It's, according to this, 1 plus 39 over 54. And now we can take that little remainder of, which is less than 1, and flip it over just as we flipped over this remainder. Okay, what would the next step be? So I'll go up here. It would be 6 plus 1 over 1 plus, okay, flipping this over, would be 1 over 54 divided by 39. And then that would be 6 plus 1 over 1 plus 1 over. What's 54 over 39? According to this, it's 1 plus 15 over 39. And we could keep going like this, and the final result okay, so we keep going one step for each one of these until we get there we go, up here, until we get 6 plus 1 over 1 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 2. That's a rather curious fraction, but okay, that's a fraction, just all sort of adds up. And sometimes this is represented now just by the sequence of the quotients, 6, 1, 1, 2, 1, 1, 2. And this is called a continued fraction. Continued fractions are useful because if you stop the process at any intermediate stage, you get a pretty good approximation to the thing you started with. So for example, if we truncate, we get a good approximation. So for example, suppose I just ran out of patience, and once I got to this step, I said, that's it, I'm stopping. I'm not going to add the little stuff that's on the end of that. If I evaluated that, what would that actually be? Well, to evaluate it, I have to sort of work from here and go backwards. So it's 6 plus 1 over 1 plus, this is 1 over 3 halves. So this is really 2/3. And this then is 5/3. So that's the same as 6 plus 3/5. Or as a mixed fraction, 33 over 5. So that would be an approximation to 612 over 93. And by going further down, we get a better approximation. By taking fewer things, of course, we get a poorer approximation generally. So the theory of continued fractions plays a big role in perhaps what's the most important equation in the ancient times. One that started off in the ancient Greek world, but was taken up later by Brahmagupta and Indian mathematicians. And it's these days called Pell's equation. It's an equation in natural numbers, so it's called a Diophantine equation. Named after the Greek mathematician Diophantus, who lived around 300 AD. And he was very interested in solving equations in natural numbers. And Pell's equation is an example of such a thing. It's the equation x squared minus n y squared equals 1, where n is a fixed non-square natural number. The simplest example is when n is 2. And that's one that the Greeks were interested in. So this is a special case of Pell's equation, x squared minus 2y squared equals 1. We're looking for solutions. We want natural number solutions. Why might we want something like this? Well, remember that we saw before that root 2 was not of the form x over y. Right? Root 2 was an irrational number. It could not be written as a ratio of natural numbers. And that's the same as saying that we can't write 2 as x squared over y squared. We can't do that. And that's the same as saying that we can't solve x squared minus 2y squared equals 0. Okay, so we can't solve x squared minus 2y squared equals 0. But this is pretty close. And if we solve this, then we'll have something that's reasonably close to square root of 2. The ratio x over y should be reasonably close to the square root of 2. Well, the ancient Greeks, Euclid realized that there were an infinite number of solutions. Infinite sequence of solutions. Such as, well, x equals 1, y equals 0. That's a solution. And they realized that there was a kind of a recursive way of getting solutions from previous solutions. And let me write it in matrix form. So let's write x, y, n plus 1 equals 3, 4, 2, 3 times x, y sub n. Okay, I'm using just a little bit of linear algebra here. Okay, hoping that you know how to multiply a matrix by a vector. Okay, so what the ancient Greeks realized is that you could, from one solution, you could generate more by essentially a sort of recursive application of the same basic principle. So for example, if we start with the equation 3, 4, 2, 3, we start with the solution 1, 0. And the matrix multiplication, how does that work? 3 times 1 plus 0 times 4, so that's 3. And 2 times 1 plus 3 times 0, that's 2. Is that a solution? 3 squared minus 2 times 2 squared, it's 9 minus 8, that is a solution. How about if we apply it again? 3, 4, 2, 3 times 3, 2. Well, now it's 9 plus 8, that's 17. And 6 plus 6, that's 12. Is it true that 17 squared minus 2 times 12 squared equals 1? 17 squared is 289 minus 2 times 144. That's equal to 1. And you can keep going. You can keep going, generating more and more solutions in this way.
Does that increase with
Sorry?
Does that get closer and closer
to root 2, yeah. So the ratio of 17 over 12 is a reasonable approximation to root 2. And if you want a better approximation, you just keep on going and you're getting closer and closer rational approximation to root 2. So this is an approximation to square root of 2. Okay, we're going to talk more about Pell's equation, but now we make contact with one of the most interesting aspects of, in my view, of ancient Greek mathematics. A remarkable document was found in a library in Germany by a dramatist, a German dramatist named Lessing, and he found a document. It was, I think, in Wormbüttel in the 18th century, I think. And it was a kind of a poetic or epigram thing that was written by Archimedes. It was a puzzle, the cattle problem of Archimedes. Okay, so I'm not going to read all of it. I'll just give you a taste of it. So here's the cattle problem of Archimedes. Archimedes, greatest mathematician of ancient times, probably the greatest mind who ever lived. In my opinion, this is the greatest mind who ever lived. And his dates are something like 287 to 212 BC. And we'll be talking more about his accomplishments. But here he is talking to us, giving us a puzzle. He saying, "If thou art diligent and wise, O stranger, compute the number of cattle of the sun, who once upon a time grazed on the fields of the Thrinacian isle of Sicily, divided into 4 herds of different colors, one milk white, another glossy black, a third yellow, and the last dappled." So there's a certain number of cattle on this island. "In each herd were bulls, mighty in number according to these proportions. Understand, stranger, that the white bulls were equal to 1/2, a half, and a third of the black, together with the whole of the yellow." Instead of saying 5/6, the ancients like to say 1/2 plus 1/3. So he's basically giving us that equation. And then he gives us 6 more equations. So altogether there are 7 equations in the numbers of bulls and the number of cows. Okay, so I'm not going to say what they all are, but there's 7 equations in 8 unknowns. The first example of a linear algebra problem. And you can look this up and you can write down the augmented matrix and you can do row reduction and figure out that there's a one-dimensional kernel, and you can try to write down what the solutions all are. First year algebra allows you to solve this system. So he ends this by saying, "So if thou canst accurately tell, O stranger, the number of cattle of the sun, giving separately the number of well-fed bulls, and again the number of females according to each color, thou wouldst not be called unskilled or ignorant of numbers. But not yet shall thou be numbered among the wise." So if you can do this first year linear algebra problem, he says, you're doing well, but you're still not really, where you ought to be. "But come, understand all these conditions regarding the cattle of the sun. When the white bulls mingle their number," so when you add the white bulls and the black bulls, and when you add the white bulls and the black, "they stood firm, equal in depth and breadth, stretching far away, were filled with their magnitude." In other words, he's saying that the white and black numbers together are a square. They have to be a square. "And when the yellow and the dappled bulls were gathered together, they stood in such a manner that their number, beginning from 1 grew slowly greater till it completed a triangular figure, there being no bulls of other colors in their midst, nor none of them lacking. So the yellows and dapples together make a triangular number. So when you solve the first part of the question, there was a one-parameter family of solutions. Now you have to pick out amongst that one-parameter family of solutions those for which the white and black bulls form a square number and the yellow and dappled bulls form a triangular number. And what does he say? He says, "If thou art able, O stranger, to find out all these things and gather them together in your mind, giving all the relations, thou shalt depart crowned with glory and knowing that thou hast been adjudged perfect in this species of wisdom." So that's the greatest mind of all time talking to us from 22 centuries ago. So what happens? Well, of course, after Lessing discovered this, people said, okay, let's do it. Let's work this out. It can't be that hard. It's just some squares and triangular numbers. We can calculate the linear algebra. That only takes us an hour. So then this second condition that Archimedes tantalizes us with turns out, after you write it all down, to become a Pell's equation. And it's a Pell's equation just like the one I gave you, but it's this form. So you get a Pell's equation, and here's what you have to solve. X squared minus 4, 7, 2, 9, 4, 9, 4, y squared equals 1. Okay, this turns out to not be so easy. So although in the theory of Pell's equation, it turns out that the difficulty of solving a Pell's equation depends dramatically on this number. We'll talk about this a little bit later. Brahmagupta, the ancient Indian, realized this. You change this number a little bit, and the problem gets a lot harder or a lot simpler sometimes. This problem, this particular choice, is very challenging. Okay, when was this problem solved? Well, in the 1880s, someone sort of figured out what it was, but he realized that you needed 40 pages to write down the solution. The smallest solution required 40 pages to write down. So he wasn't able to write it down because it was arithmetically too complicated. He was able to write down the first 20 digits and the last 20 digits, and he said, okay, and I can tell you roughly how big this is, but I can't write it down. It was only solved completely, somebody wrote down the entire solution, how many black bulls, how many white bulls, in 1965.
Did he have an answer when he wrote it?
We don't know. Probably not. But, it's some kind of amazing thing. And if you want to know more about this story, there's a lovely article it's a bit more advanced, by a friend of mine, Ilan Vardy, in the American Mathematical Monthly, which talks about, in fact, a surprising alternate formula for the solutions. So we're going to talk more about Archimedes next time when we talk about infinity in Greek mathematics. Okay, so it's really calculus or calculus ideas as the ancient Greeks thought about them. So I'll see you then.